This is part of the BocaPhysics series on electromagnetism. In today's lecture, we're going to discuss energy associated with magnetic fields. In a previous lecture, we defined what the terms mutual inductance and self-inductance mean. Mutual inductance basically describes a coupling between circuits, and self-inductance is a coupling of a circuit with itself. So those two expressions are mutual inductance is the derivative with respect to the current flowing through the J circuit of the flux through the I circuit due to the magnetic field of the J circuit. And for self-inductance, that's basically the flux, the derivative of the flux through a circuit with respect to the current flowing in that circuit. Okay? And here we're assuming that we've got a collection of, say, N circuits. We also derived an expression called the Neumann formula. So say we've got two circuits, and we focused exclusively on circuits that were rigid and stationary. In linear media. In that case, these derivatives can be replaced by just the flux divided by the current and the Neumann formula pertains to two coupled circuits. It's mu naught over 4 pi. Line integral around circuit 1, line integral around circuit 2 of dot products of the line elements R2 minus R1. There are two features here that should jump out at you. The first one of which is that this is purely geometric. In other words, there's no dependence on the current, it just depends on what shape the circuits are and how they're oriented with respect to each other. Number two, what you'll notice is that this expression is symmetric. And last time around we did an example where we calculated the mutual inductance between two coaxial solenoids, one of which was assumed to be very long, so that means of course that you can assume that you can apply Ampere's law. In that case, the magnetic field is uniform, and calculate the flux through the smaller solenoid at finite length. Pointed out that you could do it the opposite way as well. You could determine what's the magnetic field due to the small finite length solenoid and figure out what the flux is. However, that is a truly ugly calculation, whereas the former you can handle in a couple of lines. So two features here, purely geometric and symmetric. So now that we've revisited these two expressions for inductance, we're in a position now to calculate the energy associated with the magnetic field. I can figure out what, if I need to establish a current in a loop, I'm going to have to do work against the induced EMF. We're especially interested in how the flux changes with current change. flux change or flux increment through the IV circuit is equal to the summation over all the circuits that are coupled together. The derivative of the flux with respect to current times current increment. Okay, well, if you just recognize this term here is mutual inductance. So essentially, because we've assumed that the circuits are rigid and stationary, we're assuming that there's no mechanical work associated with the circuits changing shape. So any change in energy in the system is simply due to the work done on the system. Or work done against induced EMF. So basically, there's no mechanical work being done here. Okay? And there's one other point as well. We're assuming that these magnetic systems are reversible. So what does that mean? Well, generally speaking, if you have resistance in your circuit, there's going to be power dissipated in that resistance, and the amount of increment of or heat loss basically is equal to I squared R times dt. So we're assuming our system's reversible, so we're disregarding any terms of that kind. Okay? Now, because we are assuming that we're dealing with linear media here, it doesn't matter how we go from the initial state to the final state. In other words, how we go from zero flux up to whatever the final flux is. We'll bring everything up to the final state, basically in the same way. And zero flux here corresponds to current equaling zero. Okay? What that means is that any stage during this process, current at some point in time is some fraction of its final value. And alpha has value 0 initially corresponding to current 0 up to the final alpha 1, which tells us that then the current has its final value. Okay? And a similar expression holds for the flux change. So whatever the change is going to be equal to the flux times d alpha. Oh, now I'm in a position to integrate. Going from the initial and final state corresponding to alpha equals 0 and up to alpha equals 1. And let me take the limits off here for the time being. We have summation because we've got in circuits altogether. And that is the energy stored in the system or in the fields. Summation I equals 1 to n, number of circuits in the system, 1/2 current in I times the flux through I. Expanded this out, written the flux in terms of the inductance because in this case, flux through circuit 1, say, is just equal to L1 I1. And now, if you've got a single circuit, the amount of energy stored in the inductor is equal to 1/2 times the self-inductance times I squared. If you happen to have two circuits, energy is equal to the term due to circuit 1, term due to circuit 2, and the coupling between the two circuits. Now, I can come up with an instructive relation between the self-inductances and the mutual inductance between them. So I'm going to rewrite current I1 as some quantity x times I2. I'm going to pull I2 squared outside of the brackets. Now, it must be the case that the energy here is greater than or equal to 0. Well, these two terms, first and last terms, are positive. The inside term can be positive or negative. So I'm going to take the derivative with respect to x. So we'll do dw by dx. And set that equal to 0. So our extremum will occur at minus M12 over L1. And to determine whether this represents a minimum or maximum of the function, take the second derivative. That's positive just by inspection here. So therefore this is in fact a minimum. Doing the math here, see that the product of the self-inductances is always going to be greater than or equal to the mutual inductance squared. Between those two circuits. So we come up with two expressions here. Number one is one for the energy. In particular, if we've got one specific circuit, then that's just 1/2 times the self-inductance of that circuit times current squared. And then we also have this relation between the self-inductances of the individual circuits and the mutual inductance between them. Okay? Let's move on and derive a different expression for the energy, a little bit different way. Magnetic flux through the outer circuit is just equal to the surface integral of the magnetic field dotted into the normal of the surface, and I can replace the magnetic field by the curl of the magnetic vector potential, and I can use Stokes Theorem to convert this to a line integral. So that just becomes a line integral around the path that bounds this surface of vector potential dotted into the line element. Now, the amount of energy stored in this system is equal to 1/2 summation I is equal to 1 to n, where n is the number of the circuits, current that flows through circuit I times the flux through current through circuit I. And I can move current inside the integral sign. So that holds if you're talking about wires, but I'm going to generalize this expression. Replace, therefore, if I think of this instead of being a wire, but I'm taking that path following a wire, think of it following a path through a conducting medium, I can replace summation I equals 1 to n of the line integral around circuit 1 by a volume integral, and I can replace the current times the line element by the volume current density times the volume element. In this case, the amount of energy stored then becomes the volume integral over the volume current density dotted into the vector potential. This still isn't a useful expression for me, so I'm going to do a little bit more manipulation. I'm going to make use of the fact that the curl of H field is just equal to the volume current density. Because I'd rather have this expressed in terms of the magnetic field as opposed to the vector potential, I'm going to use vector identity to get there. So recall that dot product, or rather the divergence of the cross product of two vectors, regardless of what the vectors are, that is equal to the difference of H dotted in the curl of A and A dotted in the curl of H. Leave off that halves out front. And there's your expression for the energy. And one more step. I'm going to convert the second volume integral, because I'm taking the divergence of a vector and calculating the integral of it, that is can be replaced using Gauss's theorem by the surface integral over the surface that spans this volume of that vector dotted into n. Now, if I go one step further and extend surface infinitely far away, and because I'm dealing with finite distributions of current, this second term drops out, and the energy due to finite current distributions is equal to 1/2 h dot b d tau. Now, if you're just dealing with the vacuum, then the amount of energy is equal to 1/2 mu naught integral volume integral of b squared. Notice the similarity between this expression of the energy stored in magnetic fields and this expression for the energy stored in electrostatic fields. That's epsilon naught over 2 volume integral of E squared in this case. So definitely takes work to establish currents to set up a magnetic field, but yet magnetic fields don't do any work. So how do we explain that? Well, the thing of it is, as the magnetic field is changing in time, an electric field is induced, and that is the mechanism that is actually doing the work on the system. Okay? I'm going to do a few examples. The first example I'm going to work through is calculating the energy stored in a finite length of a very long straight solenoid. Therefore, the magnetic field inside is equal to mu naught times the number of turns per unit length times the current in the z direction. And 0 outside. Answer this question two ways. First of which is just this expression, 1/2 times the self-inductance times the current squared. amount of flux through this segment is equal to magnetic field, which is uniform, and that's why I can just have a product rather than do an integral, times the area. So we'll assume that this solenoid has radius r, and then we're interested in a certain segment of length L. Well, there are number of turns per unit length times length L is the number of turns in that particular segment. And therefore the inductance, self-inductance of that segment is equal to mu naught n squared I times pi r squared. And therefore the amount of energy stored is equal to, I'm sorry, I should not be there, it should be an L instead, so that's mu naught n squared L times pi r squared, and therefore the amount of energy is equal to mu naught little n squared times L times pi r squared times I squared all over 2. The other way of determining the amount of energy stored is to use this expression. One over 2 mu naught b squared times integrating over the volume. Now, once again, magnetic field is uniform, so that's 1 over 2 mu naught times 2, or rather, n mu naught I quantity squared times the volume. The volume of this segment is just going to be pi r squared times L. And we lo and behold wind up with exactly the same answer. So as in many times in physics, there's more than one way to solve a problem. And this suggests a technique, actually, for calculating the self-inductance of a certain object. If you can figure out what the energy is stored in the magnetic fields, and then use this expression to determine what the self-inductance is by setting this equal to this, which is useful in certain circumstances. Okay? Next example I'm going to work through isn't really about calculating the energy, but it's interesting because it really is how you treat transmission lines. And so what we'll assume is that we've got current flowing in one direction on the upper sheet and in the bottom direction the other sheet. So we'll assume that they're separated by a distance d, their length L, and width W. My goal here is to calculate what is capacitance per unit length, and then what is the inductance per unit length. Now, if we just look at the capacitance, well, that's just geometric quantity. It's just equal to the area times epsilon naught, permittivity of free space, over the separation of the plates. And the area of the plates is just the length times the width. And so therefore our capacitance per unit length is just W epsilon naught over D. Now what about the inductance per unit length? Well, we need to know what the magnetic field is. So between the plates, that's just equal to mu naught times K. And K, of course, is the surface current density. Which is equal to the amount of current per width. Magnetic field in this case is pointing into the board. And if we construct a surface, the amount of flux that passes through that surface is equal to mu naught I over W times length times d. And for the inductance, it's just equal to the flux divided by the current, which is mu naught L d over W. And if we want to know what the inductance per unit length is, that's just mu naught d over W. I take the product of the inductance per unit length and the capacitance per unit length. Look at what happens here. The actual dimensions of the transmission line cancel out, and that's equal to mu naught epsilon naught. And what's that equal to? Well, if we do 1 over square root of that quantity, that's just equal to the speed of light. So, interesting thing there is that this is actually a constant, independent of the actual dimensions. And 1 over square root of it is equal to the speed of light. Now through a couple of circuit problems. First of all, we'll do an LR circuit, that is to say a circuit that has an inductor and resistor in series, and then we'll also the last 3 examples I'm going to work through are circuit examples. In the first case, we'll consider the last 3 examples that I'm going to work through are circuit problems. In the first 2 cases, we'll deal with a circuit that has both an inductor and resistor in series, and we'll look at what happens once the circuit is closed, and then if the circuit's been closed for a very long time, what happens once it opens up. And then we'll also look at an LC circuit as well. First case, let's suppose we've got a battery and we've got a switch here. We got a resistor and an inductor. Right after I close the circuit, or the switch rather, current's going to begin to flow. But this isn't going to happen instantaneously. In fact, immediately after the switch is closed, amount of current flows is equal to 0, but then it will build up. After the switch has been closed for a very long time, Well, there'll be no change in the current. It'll reach a steady value, and basically I is just going to be equal to the EMF provided by the battery divided by the resistance. So let's write down Kirchhoff's loop rules that applies in this circumstance. So we have EMF minus the contribution from the resistor, so that's current times resistance, and then we got the contribution from the inductor, which is L di by dt. I'm going to solve this expression for the current. I want to gather all the I terms on one side and the dt, the time terms, on the right-hand side. And what I'll do too is basically multiply both sides through by the resistance, and that'll be di over I minus the EMF over the resistance minus resistance over inductance dt. And I'll integrate this from some initial time 0 up to some final time t. And initially, there is no current flowing right after the switch closes. The current can't change instantaneously, so that's going to be 0. And if I do the math here, this will give me natural log on the left-hand side of I minus EMF over resistance divided by minus EMF over resistance. On the right-hand side, that's just equal to minus resistance times time over the inductance. I'm going to solve for the current. That's what I'm after all. So if I take the exponential of both sides and then I can multiply both sides by minus EMF over R, eventually I would wind up with EMF over resistance of 1 minus e to the minus RT over L. And that's how your current behaves after you've closed the switch. So at time equals 0, the second term is 1. So you basically have 1 minus 1, and therefore the current's equal to 0. After the switch has been closed for a very long time, so in other words, as t approaches infinity, this term goes to 0, and you're just left with the current is equal to EMF over the resistance. Because the current is no longer changing, there's no more EMF being induced inside of the inductor. If I want to look at how the rate of change of the current, well, I just take the derivative, and that's equal to EMF over the inductance times e to the minus resistance times time over inductance. And as you can see, at t equals 0, the rate of change of the current is just equal to the EMF divided by the inductance. And as time approaches infinity, after the switch has been closed for a very long time, the rate of change of the current goes to 0. And to sketch out what the current looks like, well, it starts out at 0, but approaches some limiting value here. And that limiting value is just equal to the EMF over the resistance. Now let's suppose that we have an inductor and a resistor that have been hooked up to a battery for a very long time. So in other words, now we're interested in current decay. basically what you want to imagine is that, so you got a switch up here that's been closed for a very long time. You got another switch here that's open, okay? So this has been, battery's been hooked up, so you're going to have a steady flow of current. However, I'm going to open this switch up and then close that one. So effectively, I'm removing the battery from the circuit, and by applying Kirchhoff's loop rules, equation to solve for is going to look like this. I no longer have the battery hooked up, so these two terms are just going to be equal to 0. I'm going to solve for the current again, the same way I did before. So I pull all the current terms over to the left-hand side and the resistance terms, or rather the time terms over to the right-hand side. And if I solve this, I'm starting from time t equals 0 to some future point. And then I'm also going to say, well, we start out with some current I naught and up to some final value at some time t. And once again, I want to take the exponential of both sides, and then I'll multiply through by I naught. And therefore, your current goes as I naught e to the minus RT over L. Well, what's I naught equal to? Well, that's after, say, this switch was closed and this one's open. It was hooked up for a very, very long time. So basically, the current that flows was just equal to the EMF provided by the battery and the resistance of the resistor. So at time equals 0, the amount of current that flows is going to be equal to I naught. After an infinite amount of time, the amount of current that flows is equal to 0. And I can also look and see how the current changes in time. That's just going to be equal to minus I naught R over L. But I naught is equal to EMF over the resistance. So the rate of change is just going to be equal to minus EMF over the inductance times e to the minus RT over L. Okay? And if you looked at what that current looks like, it would start at some value I naught and decays exponentially and goes to 0 after an infinite amount of time. Where does the energy come from to maintain the current? Well, there was current flowing in here. Work had to be done against the induced EMF, so there's energy stored in this magnetic field. And that amount of energy that was stored in there initially is equal to 1/2 L times I naught squared. So once you disconnect the battery, you'll still have a current flowing for some time, and that current is going to be dissipated in the form of heat. So I'm going to calculate the amount of energy dissipated in the resistor. That's just equal to I squared times resistance times dt. We just figured out an expression for the current. It's I naught squared times resistance. So we could put this on the next line because I'm running out of room here. So this will be I naught squared times the resistance, evaluated from 0 to infinity, and this is e to the minus 2 resistance times over inductance dt. And of course you have a factor of 2 there because you're squaring the current in the integrand. Okay, so I do the math here. This is I naught squared times resistance and I evaluate this at time equals infinity, it's equal to 0, of course. If I evaluate it at 0, this exponential is just going to give 1, so I've got minus minus, and I'll wind up with L squared over 2, or I should say L over 2 times I naught squared. So that was the energy that's dissipated in the form of heat in the resistor. That energy, after we disconnected the battery, came from the energy that was stored in the magnetic field. Okay? And let's move on to one last problem in today's lecture. The last circuit that I'm going to consider today is an LC circuit. So I've got a capacitor hooked up to an inductor. I'm going to assume that at time 0, the capacitor is fully charged. Well, that capacitor is hooked up to an inductor, so current's going to flow. But that current flow can't change instantaneously. So basically at time 0, current that flows is going to be equal to 0, but it will reach some maximum value. So there's an electric field in the capacitor, and if there's an electric field there, there's energy stored in this field. Okay? So the capacitor is discharging after time 0, and the current is building up, so the magnetic field is also building up, and there'll be an induced EMF in the inductor tending to oppose that change. Okay? So, well, this is discharging, and the energy in this electric field is decreasing. The energy in this inductor, or energy in the magnetic field associated with the inductor, is going to increase. In fact, the amount of energy here, when this is current flow is equal to 0, will be equal to the amount of energy stored here when the current is at its maximum. So once it reaches its maximum value, it can't again change instantaneously. It's going to persist. So the capacitor is going to start charging once again. But again, your current flow, or your rate of current flow, is changing. So the magnetic field changes, the magnetic flux changes, there's an EMF induced that opposes that change. This time around, because the magnetic field is decreasing, there's going to be the induced EMF, which tends to oppose that change, is actually going to be going in the same direction as the current. So anyway, the bottom line here is that you won't see exponential behavior. This behavior is oscillatory. And because we're assuming that there's no resistance in the circuit, there won't be any energy loss to Joule heating. If I apply Kirchhoff's loop rule, I've got a term associated with the inductor, and then I've got a term associated with the capacitor. So I've got minus L di by dt minus Q over C. Now, current is equal to the derivative of charge with respect to time, or basically another better way of saying it, I suppose, is that current is equal to the amount of charge that passes a certain point per unit time. So anyway, if I plug this into here, what I'll have is a second order differential equation. Second derivative of charge with respect to time plus Q over LC is equal to 0. Lo and behold, this is just the equation of a simple harmonic oscillator. In that case, I can set omega squared equal to whatever LC, and therefore, the equation, second order differential equation to be solved is second derivative of q with respect to time plus omega squared times q is equal to 0. If I do the math there, q is just equal to big Q cosine omega t plus phi. Current is just the derivative with respect to time. And that's minus omega q sine omega t plus phi. Now our initial conditions were that the capacitor is fully charged at time equals 0. So if I take time equals 0, well then that corresponds to a phase equals 0. So then q is equal to big Q at time equals 0. That's what we want. And the current correspondingly, or time equals 0, and phi chosen to be 0 as well, is just going to be 0. So that stage capacitor is fully charged, and then current begins to flow, and eventually we'll reach some value I max. So that concludes an LC circuit problem. You could have resistance in here as well, in which case you'd have to deal with critically damped systems, overdamped systems, and underdamped systems.